Hey guys, in this video we're going to talk about finding volumes of known cross sections, and that's when I have a solid and I know the shape of the cross-sectional area, and I'm going to find the volume of that. So we're going to start with this idea that whenever I find volume of something, think about this like a stack of Ritz crackers, I would find the area of the base, which here is a circle, and multiply it through by the height because I'm stacking up those cross-sectional areas. Same thing with any of these, right? Any prism, you're doing area of the base times the height because you're stacking up your cross-sectional areas. So this idea is really key. Volume is the accumulation of cross-sectional area. It's accumulating over the height of that shape. If you add up the volume of each slice, you can find the total volume of the solid. So just visualizing some of these, because again, they're a little hard to visualize. So this is a two-dimensional area here between these two curves. Let me color that in. And what I'm doing is I'm laying squares on top of it, right? And when I do that to a solid, it's going to look like this. And so it's a weird looking solid, but we can find the exact volume of that. Same thing here. I have that same two-dimensional area, and I'm going to lay equilateral triangles on top of it. And that's going to look like this solid once they're all stacked. Same thing on this one, same base area, but I'm laying semicircles across the whole thing. So if I stack up all those semicircles, it would look like that, curved on the top. So we're going to find the volume of those, and we're going to think about it using these formulas. That volume is the accumulation of area with respect to x or with respect to y. Thinking about this as your base area, and then either your dx or dy as your height, because remember that's your change in x or your change in y. How do you know whether it's dx or dy? The same way we did with area between curves. Dx is going to have the delta x as your height of your slices. Dy would have your delta y. So I always say if it's slicing the x-axis, it's dx. If it's slicing the y-axis, it's dy. So let's look at an example. We're going to work on setting these up. If you need more help with actually doing this integration, that's something that you want to look back at some basic u substitution or integration techniques for. But this says region B is bounded by the x-axis, x equals 9 and y equals radical x. Bases of cross-sections are perpendicular to the x-axis. So this is my region, and when I put a cross-section on it, and I'm drawing this in 3D, but it's going to come like this, and let's say these are semicircles, right? It would look like that, lying three-dimensionally coming out of the z-axis. Same thing here, let's say it was squares, so squares would come out like this, and I'd be setting them on that region perpendicular to the x-axis. So let's see what our first region looks like. So what is the volume of a solid with square cross sections? So let's think about what that would look like. Again, we just kind of sketched it, but it's going to have squares lying like this, and they're going to be bigger or smaller based on the size of that initial side that we laid down, right? Over on the left side all the way over, they'll be smaller versus over here on the right where there's a bigger initial side, they'll be bigger. They get bigger as we go. So what we need to think about there is, well, what is the area of a square? Because we know that volume is the accumulation of area, and this is going to be with respect to x because it's dx. So I need to think about what my area would be here. So area of a square is side squared, right? And let's look at the length of one side. So the length of one side here, S, would be my top minus my bottom, right? So square root x, and the bottom function is just 0. So this would just be square root x minus 0. So your area function here is square root x minus 0 squared, or just x. It's your area function. So knowing this, knowing that my area of a square is side squared, and a side length is just square root of x, the area function would be that squared, or just x. So what I'm going to do now is integrate that for the volume. So volume is going to be the integral of, we know it's the area function, which is just x, dx. And what are my bounds? Well, this region starts at 0 and ends at 9, so this would be from 0 to 9. Okay, let's try another one. So what if we use semicircular cross sections? So same region, right? Same region, but now instead of putting squares on it, I'm putting semicircles on it. So those are going to look like this, right? An area of a semicircle here is 1/2 pi r squared. right? 1/2 pi r squared. So what I need to do is figure out what my radius is. So thinking about this circle, radius would be from there to there, right? So the whole diameter here would be square root x minus 0. The radius is going to be half of that. So your radius here is square root x over 2. And I'm going to plug that into my area function. So your area here is 1/2 pi times radical x over 2 squared. So that's my area function. So you can simplify that down a little bit. You could make this area is pi over 8 radical x. That would make it easier to integrate. And so I'd be doing the integral from 0 to 9 of pi over 8. You could bring that out to the front. X dx. I don't need that radical there because I squared it. Okay. So let's look at this one. What is the volume of solid with isosceles right triangles as your cross section? So these are right triangles, and we know that they're isosceles, so these two legs are congruent, and that's convenient because that's the base and the height of this triangle. So looking at my triangle here, I know that area is 1/2 base times height, which in this case is just 1/2 base squared, side squared, whatever. So it's going to be 1/2 my side length squared, because those are isosceles. And my side length is that same square root of x. So this area function is 1/2 square root of x squared, so it's 1/2 of x. So when I integrate this, it would be the integral from 0 to 9. The 1/2 can go out front, x dx. And so I would get different volumes for each of those based on what type of cross section I'm getting there. So let's look at another one. So now region C is the bounded area by y equals 9, y equals x squared. Bases of cross sections are perp to the y-axis. So now I'm looking at cross sections that go like this, and they come out like on the z-axis three-dimensionally, right, off of this region. And so now because I'm cutting the y-axis, these are going to be dy. So the first thing I want to do is kind of look at my region, figure out what my bounds are, go from there. This part here, thinking about my y bounds, that's 0, 0. This up here is 0, 9. So my y bounds here are going to go from 0 to 9 because that's my y values. And then I'm going to think about my curves. So yes, this is y equals x squared, right? But I want this in terms of y because I'm going to use dy. So x would equal plus or minus radical y. So this side would be positive radical y, and this side would be negative radical y. So when I look at the distance across this, the side length, right? So what I'm actually going to be getting here, doing right minus left, is the square root of y minus the negative square root of y, because I'm doing this side minus that side, and that's going to give me 2 radical y. So that is my side length there. So volume with square cross sections. Remember, area of a square is your side length squared. And my side length here is this, the region there. Thinking about putting a square on top of there. So area of a square is going to be the side length squared, which we determined would be 2 radical y squared. And so my area function, yes, you can just use that, or you can make it 4y. So this would be the area from 0 to 9. Remember, integrate your y values of 4y dy. You could bring that y out to the front before you integrate it, and you'd be fine. Let's look at another one. Let me erase this square here. So volume with semicircular cross section. So now I'm talking about putting a semicircle here, right? So area of a semicircle is 1/2 pi r squared. What's your radius here? Well, you can either take your whole side length and divide it by 2, which would just give you radical y, or you can think about from the center to the edge there, that's just radical y and 0. So your radius there is just radical y. So this would be 1/2 pi times radical y squared. So your area function is 1/2 pi times y. And so I'm going to have the integral from 0 to pi of pi over 2. That can just come out to the front, y dy. Actually, that should be bounds from 0 to 9. Remember, we're looking at y values. All right, last one. What is the volume of a solid with rectangles where the height is twice the base as cross section? So let's think about this. Think about this rectangle where, and actually I'm going to draw it a little differently. Let's say that's our base, that's our height, and what they're saying here is height is twice the base. So the area function here would be base times height, which would be 2 base squared. So we just need to know what that base length is, right? So your base length, again, if you're placing this on top of this region, your base length is that distance right there from the right to the left. So that base length is going to be 2 radical y. So this would give me 8y, square both parts. So I would have the integral from 0 to 9 of 8y dy. Again, that 8 could just come out to the front, and that's totally fine. So this is your summary. Again, this is in your notes packet, but perpendicular to the x-axis, you're using dx. Perpendicular to the y, you're using dy. If you guys have questions, let me know, and I will see you guys soon.